Yamamoto of Kochi University of Technology. First of all, I'd like to thank the organizers to give an opportunity to talk about material design of wide bandgap oxide semiconductors at this conference. Okay. In this talk, I'd like to propose a new look at oxides. First is electronics, second is transparent conductors, and the third is the radiation-resistant materials for the space industry in the foreseeable future. Okay, and the last is the biological and the medical applications. Today, in the time of interest, I'd like to focus on the electronics, transparent conductors, and the biological and medical applications. Okay. First, I'd like to show you the electrical applications concerning the power electronic devices. Okay. Power electronics is a branch of electrical engineering that deals with the processing of high voltages and high current, okay, to deliver power that supports a variety of needs. And in this talk, and the keywords as follows: gallium-203 and the breakdown field, okay? This slide shows power devices in more detail, okay? High efficiency power conversion will be required for energy saving in the near future, okay? And the left-hand side figure shows a crystal structure of a beta-type gallium-203 presented by Dr. Higashiwaki in Japan. And the right-hand side figure shows a power frequency diagram of the application space, okay, for several semiconductor materials, such as silicon carbide, gallium nitride, and gallium-203 and gallium arsenide and indium phosphorus, okay. And I'd like to discuss the criteria used to compare the different wide bandgap materials, such as silicon carbide, gallium nitride, and gallium-203 presented below, okay, with properties that improve the characteristics of the electronics converters based on three factors, okay. First is electrical properties, and second is the thermal properties, okay. And last is material availability and the manufacturing cost. This is the most important and very important topics from the viewpoint of industry based on my experience on the industry, okay? This slide, this table shows a comparison of beta-type gallium-203 to other prominent semiconductor materials, silicon, gallium arsenide, silicon carbide, and gallium nitride, okay? As you can see, okay, the beta-type gallium-203 shows a wide band gap of 4.8 to 4.9 electron volt, okay? And please note that, okay, the breakdown field, okay? The beta-type gallium-203 exhibit high breakdown field, okay? And then the various figure of merit, this is the most important parameter for the power electronic devices, okay? The beta-type gallium-203 shows a high various figure of merit of 3,000 or more than 3,000, okay? Due to the large values of the breakdown field. And I'd like to discuss, okay, the comparison of the most important properties of semiconductors for smart grid applications. The important properties include frequency capability, manufacture, availability, and maximum operation temperature, okay? and the best material for high frequency applications and some limitation of the transistors. Okay. As you can see, silicon has most advantages, manufacture and availability, okay, to the other materials. This is very important, okay, properties. Okay. On the other hand, concerning the frequency capability for a transistor, for frequency applications, the beta type gallium-3 showing a high critical breakdown field will have the highest breakdown field and high switching speed. Okay, node of switching speed. Okay. However, beta type gallium-3 has issues to be resolved. That is the poor thermal properties. Okay. And then due to the poor thermal behavior, to date, the applications with the soft switching converter. Okay. And then I'd like to know that for achieving wide pulp device applications of wide bandgap oxides, whereas holding a competitive cost, it is mandatory to increase the switching frequency above the limits of silicon, together with an improvement in thermal conductivity. Our biggest concerns is what dominant factors limit the thermal conductivity. Okay. And I'd like to move on to the optoelectronics. And concerning the ultraviolet wavelengths, okay? The first is the deep ultraviolet wavelengths ranging from 0.2 to 0.35 micrometer. Applications includes water disinfection, sterilization, resin curing, and biotechnology. Okay. And Kaneko-san reported a successful seal, a spectra of a magnesium, a zinc oxide thin films with a wide bandgap of 5.1 electron volt deposited on the magnesium oxide substrate. Okay. And next is vacuum ultraviolet wavelengths of more of less than 200 nanometer. As you know, the ASM company, so the big company, okay, due to the successful development of EUV, okay. And the candidate materials is limited, just only oxide, not nitride, okay? And the candidate materials is oxide semiconductors, such as magnesium oxide, magnesium zinc oxide, and aluminum gallium 2O3. And Onuma-san reported a free and bound existence emission of magnesium oxide single crystals in vacuum UV spectral range. Okay. Okay. And now I'd like to move on to the transparent conductors. So this is my field. Okay. This I'd like to show you the sheet resistance ranges of transparent conductive performance for various applications, such as the touch screen, smart window, flexible LCD, and flexible OLED, and LCD television, and the photovoltaic solar cells. As you know, sheet resistance determined by the electrical resistivity, film thickness, especially home mobility, that is area transport properties. Okay. And the research group in Korea proposed the room temperature process high mobility tungsten doped indium O3 IWO electrodes for flexible OLEDs and the quantum dot LEDs. The point is, okay, room temperature process. Okay. And on the other hand, in our laboratory, we proposed a successful fabrication of the display of LCD television mounted with a gallium doped zinc oxide-based transparent electrode prepared on RDBY color filter. Those televisions fabricated by the Sharp Corporation using the conventional mass production lines. Okay. And the point is low temperature deposition due to the weak heat resistant color filter and reduce the damage to the underlayer. Okay. And we find the for those LCD television enhanced brightness by 5% compared with those the conventional LCD television mounted with an ITO, the ITO electrode. Okay. And very recently, we deployed high efficiency silicon heterojunction solar cells, which has been already commercial, okay? And it's showing efficiency of 24.1%, okay? And concerning the cerium and the hydrogenated individual O3, we find a high hole mobility of 155 centimeters square per Bosecond at a carrier concentration of 2 times 10 to 20 power per cubic centimeter. And the critical, okay, technology is a solid state crystallization from amorphous obtained at the room temperature to polycrystalline line phase after the post annealing, okay. And in our laboratory, we have been developing the deposition technology collaborated with Sumitomo Heavy Industries, okay, that can suppress damage to the substrate surface and growing the film. This photograph is within the apparatus and arc plasma. Okay. And I'd like to show you the comparison of coating techniques. RPD is another technology, reactive plasma deposition with a DC arc discharge, okay? And conventional coating techniques, as you know, the magnetron sputtering, DC or RF sputtering, and plasma enhanced CVD. The features of the RPD show the high plasma density as well as a magnetron sputtering. And as you know, as you can see, another of the features is very narrow windows as well as plasma enhanced CVD. Okay. And this is a schematic diagram of the RPD with the traveling substrate. And the apparatus does work very well because of high growth rate, typically 170 nanometer to 200 nanometer per minute, okay, produced by Sumitomo Heavy Industries. And this is a photograph of the RPD in our laboratory, okay? And the maximum sample size is 50 centimeter cross 50 centimeter, okay? And this is a photograph of RPD for use in the mass production lines produced and provided by Sumitomo Heavy Industries, okay? I'm not a salesman of the Sumitomo Heavy Industry, okay? And I'd like to move on to the main topics of my talk. Two topics, zinc oxide and the indium oxide films using the nanometer thick oxide films, okay? The first is zinc oxide. Okay, this is a crystal structure with a big, with a Uruzite structure. The zinc oxide has small values of refractive index in the visible wavelength region. And then zinc oxide-based film, thin films shows high transparency in the visible wavelengths because of the wide direct band gap of 3.37 electron volt. Okay. And I'd like to discuss how to choose and how to select n-type dopants. Okay. This is a periodical table. Okay. This periodical table provides us very impressive information concerning how to choose the elements attractive interaction with oxygen atoms. As you can see, zinc elements show the medium strength interactive interaction with oxygen atoms. And then to achieve the reliable solid-state devices, we must dope the strong interaction, attractive interaction with oxygen atoms using the aluminum, gallium, or titanium. Okay. And I'd like to show you the calculated differences of mine in the lattice energy, the amount of energy between undoped and N over P-type doped zinc oxide of crystal. As you can see, P-type doping using nitrogen, lithium, and arsenic elements. As you can see, we find an increase in the lattice energy and then result in a unstable P-type zinc oxide. It is unipolarity problem. On the other hand, okay, N-type doping of aluminum, gallium, and chlorine, okay, you find a distinct decrease in the modern lattice energy. And then the doping, N-type of doping, so there's a very stable thin films, especially gallium elements will play a critical role as an oxygen stabilizer in the N-type doped films. And I added the balance shell orbital radius, S and P orbital. As you can see, aluminum elements show the long S and P orbital. Okay. And then in the aluminum doped zinc oxide films, we will observe very high carrier transport. Okay. And then based on the calculated results using the ab initio electric calculations, okay, our laboratory has been developing the multi-step deposition method. DC, okay, the conversion of DC magnetron spattered aluminum doped zinc oxide films shows a large angle grain boundaries, reducing the carrier transport, okay, at the grain boundary. And then to resolve the issues, we prepared the partially just 10 nanometer thick gallium doped zinc oxide films with the 0001 orientation. Okay. And successfully, we grow the thick aluminum doped zinc oxide films. In such films, we find small angle grain boundaries, okay, well-defined 0001 orientation. And we find improved hole mobility. And as a result, we reported a successful fabrication of the display of LCD television mounted with aluminum and gallium doped zinc oxide-based electrode. Okay, and I'd like to note, in case of a polycrystalline zinc oxide films, columnar growth with preparation of 0001 orientation is favored energetically. And a little contribution of the grain boundary scattering to the carriers is essential. to achieve high hole mobility. Okay. And next is just 5 nanometer thick N-type polycrystalline line in the O3 films. And this is a crystal structure of the intimate O3 with a cubic system and the big spider structure. As you can see, we find high density of the structural oxygen defect sites, point defect. This is a reduced killer of the carrier transport. And you see the bond dissociation energies in the atomic molecule, indium oxide, tungsten oxide, tin oxide. As you can see, tungsten elements shows a high oxygen affinity. And then the use of the tungsten doping, okay, will suppress the generation of excess oxygen vacancy, a killer, okay, of the carrier transport. And this is a schematic diagram of RPD. The point is to prevent agglomerate deposition of low melting point metallic indium at in the interfaces of filaments and the substrates. Okay. And another very important technology, critical technology, is how the control the energy of the flying particle. In this work, we optimized the flying particle, especially single-charged indium plus ions. Okay, there's the fixed the 55 electron volt. Why? I'd like to show you the answer to the question. This slide gives the answer. Low damage to the surfaces of substrates and the filaments. Okay. Point is reduced energies of flying particle. This is transport energy is 25 electron volt. Above 60% of this energy goes into the thermal energy conversion, the surface of the substrate or growing filaments. The remaining energy of just 10 electron volt contributes to the following two diffusions: surface diffusion and bulk diffusion. You find no excess energies of the flying particle, okay? And low damage, no excess energy, okay? And this is an experimental result of out-of-line two-seated X-ray diffraction profiles of solid phase crystallized IWO tungsten doped into the oscillating filaments with different thicknesses, 5 nanometer, 7 nanometer, 10 to 20, and 15 nanometer. You find the with a strong intensity of 2 to 2 refractions. In other words, the directed crystallization, in which crystallization is favored in 111 directions of crystallized. And I'd like to note again the solid phase crystallization. Okay, the condition is under vacuum. And for 30 minutes at 250 degrees C. Okay. And I'd like to show you the mass density, surface roughness, and interface roughness determined by the XRR technique. As you can see, mass density and interface roughness, you find a little differences between amorphous and polycrystalline IWO filaments, okay, regardless of the film thicknesses. On the other hand, very interesting results, okay, the controlled properties, surface roughness. The surface roughness of polycrystalline IWO filaments is lower than the surface roughness of amorphous IWO filaments at any given filament thicknesses. Okay, and this will be discussed later. how to call this, okay? And I'd like to show you the structural properties and electrical properties determined by Hall effect measurements of amorphous and polycrystalline line IW films. You find the typically classical size effect model with decreasing film thickness, electrical resistivity of amorphous IW films, sharp increases. This is a typical classical size effect model. Okay. And please focus on the very thin filaments of less than 10 nanometer. With decreasing film thickness, okay, carrier concentration changes a little, whereas Hall mobility sharply decreases. Okay. Surface scattering likely change from diffuse to specular. Okay. And I'd like to discuss two different kinds of the approaches. First is classical size effect model approach to the IW filaments, okay, with thicknesses of less than 10 nanometer. This is a critical size effect model. Based on the model, the lifetime of carriers of the filaments can be expressed as follows. Lifetime of bulk, surface, and the interfaces. Okay? And using this equation, we obtain the carrier mobility of the filaments can be expressed as follows. This is the carrier mobility of bulk, bulk. And the most important parameter, gamma B, is a corresponding ratio, thicknesses, and the mean free path of electrons. And the most important parameters is the specularity parameter, P and Q, P surfaces, Q at the interfaces. In case of the specular scattering, no loss of the electron movement, okay? You find the total values of P plus Q are just practically 2, okay? And then we find on this term, it can be neglected. In such filaments, the carrier mobility of the filaments is practically equal to the carrier transport of arc. Okay, this is ideal state. And on the basis of the analysis of the expression data, film thickness decreases from 10 to 5 nanometer. The total values P plus Q decrease gradually from 1 to 1.6 specula. This this equate and implies the scattering mechanism in the change from specular, no loss of, okay, and the diffuse scattering. And then we find the carrier transport reduction with decreasing of the film thickness. And what occurs, okay, at the surfaces of and interfaces of IW films. This is an experimental fact, okay. I'm afraid that this slide shows very busy, okay. This slide shows the result of high resolution RBS and elastic recoil detection analysis, giving the hydrogen depth profiles. This is amorphous and this is polycrystalline films. Okay, just solid phase crystallization changes. For the amorphous IW films, you find oxygen rich. And as a result of the post-annealing, the film bulk, okay, changes to the oxygen poor. Whereas the oxygen, okay, we find a high density distribution of oxygen atoms near the surface and the interfaces. Okay, this is a cause of the diffuse scattering at the surfaces and the interfaces. And then, in such case, we find the whole mobility or carrier transport decreases with decreasing the film sequences. Okay, and we successfully achieved polyclonal sunlight either blue thalamus showing a high whole mobility. Okay, and the issues to be resolved as follows. We must tailor the scattering mechanism and the surfaces and interfaces. Okay. Okay. Recently, we have been developing the process of solid phase crystallization for wide applications. Okay. And okay, the last is the biological and the medical applications. This is the last presentation. Okay. The idea I'd like to note of the antibacterial is to control the activity of the micrograms and take measures to prevent the number of bacteria from increasing in the initial state. This is the idea, okay? And the use of the reactive oxygen species such as hydrogen peroxide, superoxide, and hydroxyl radical is the crucial issues for developing the antibacterial materials. And as you know, silver plus, zinc 2 plus, and copper 2 plus ions exhibit excellent antibacterial ability. Okay, this table shows the Staphylococcus aureus and the Escherichia coli. Okay. And I'd like to first propose, okay, the possible antibacterial mechanism. First is to enter the cells through the ion channel created by the God. Okay? Cross channels across the bacterial cell membranes. Second is to induce the formation of hydroxyl radical chain transfer. Okay. And in our laboratory, our work is follows. Disruption of bacterial membranes with hydroxyl radical from inside zinc using the zinc plus and outside hydroxyl radical, the breaking of the cell fragments into secular substances such as potassium ions, okay, are eluted, which is thought, okay, important word, thought, to lead to cell death. Okay. And using the ab initio electric calculations, this is a model, okay, developed by a group, okay. The future of antibacterial activity of conductive zinc oxide films, anti-static conductive, no observed hydrocarbon in the air. Okay. Point is, the generation of zinc plus ions together with the generation of the reactive oxygen species, okay? And I'd like to show you the experimental results. The first is Staphylococcus aureus. After 24 hours, okay, just use the bare glass substrates, we find an increase in the number of the living Staphylococcus aureus. Okay. On the other hand, the use of the glass substrate with conductive gallium doped zinc oxide of thalamus. As you can see, we have no detection of the living Staphylococcus aureus. In fact, within 1 hour. Okay. And the second is the Escherichia coli. In this case, okay, oh, sorry. In concerning the Escherichia coli, okay, we find an very sharp increase in the number of the living of the Escherichia coli. On the other hand, okay, DDO or coated glass substrates call this no detection of the living Escherichia coli within 1.5 minutes. Okay. And I'd like to show you a review on enhancing the antibacterial activity of zinc oxide, the powder, okay? Mechanism and the macroscopic investigations, okay? And I'd like to I show you the antibacterial activity of zinc oxide with the performance and nanoparticle. And the applications increase biomarker of oxidative stress. And in this talk, I talked about electronics, transparent conductors, and the biological and medical applications. Point is as follows. Key factor limiting the thermal conductivity in oxides, okay? And a dominant factor determining the carrier transport of the polycrystalline films. And key factor governing the generation of reactive oxygen species, okay? And as a final remark, I'd like to mention main law of our scientists, okay, on sustainable development. This is a critical material strategy proposed by from the United States, okay, and the Clinton Hillary, okay. And I'd like to note that the future supply and the demand for materials may differ from current scenarios due to breakthrough in science and technology. Okay, and I thank you for your kind attention.